Hi, this afternoon I am going to present my time series midterm models that I ran for the driven data competition to try and predict the probability of people donating in March of 2007. Um, the driven data, supposed to be, while this data set was relatively easy to deal with in terms of outliers and missing data and things of that nature, there were some complexities that we had to deal with that we'll go through a little bit later on in the analysis. So the first thing we wanted to do that I wanted to do was just upload the data, the training and the test data, and get a little bit of a better sense of what I was dealing with. Um, the summary statistics don't show anything super interesting, I didn't think, except for this one potential outlier right here of max 12,500 cc's of total volume donated. Um, while that potentially seems extremely high for the amount of to give an extremely high amount of blood to give, considering that the 75th percentile right here is only 1,750. That seems really high, but again, it's only one observation, as we'll see later on in some box and whisker plots. Um, Again, this number of times donating, the max being 50, appears to be much higher than the other ones as well. So potentially this is just somebody who has given a lot of blood and not a typo due to the fact that these two seem to go hand in hand. Number of times donating, total volume donated makes sense. So I think I'm going to leave that as is and not do anything to it, especially since we're going to be using a lot of machine learning algorithms that can deal with outliers and things of that nature relatively well. So since this is a classification problem, one of the larger issues with the target with dealing with this is having unbalanced data. So as you can see here, we looked at the total distribution of the data that we were looking at, and it seems to be an extremely high imbalance. As you can see here, 76% of the people in the population were not donors, while only almost 24% were. So before we did anything else, I needed to use the rows package and oversample on the donated variable. So I just doubled the sample size, and then as you can see here now, we have for the training data, we have a much more even split, almost 50-50, and then it's almost 50-50. I then split this data into a train and a validate set, just because I don't want to deploy the models on the test set without being able to see if it's communicable to outside data. So I took the oversampled train set, split it into a train and a validate set, and then re-graphed it to make sure that both samples still had a close to 50-50 distribution between donated and didn't donate, and they do. From here, I ran some EDA just with box and whisker plots to try to see which of these continuous variables potentially had good separation on the classifier. So as you can see here, I usually use this to see if there's a difference between the people who didn't donate and the people who did donate on these continuous variables. And it looks like all of these, except for months since first donation, are potentially strong predictor variables. Again, the next thing I did is I did check the correlation between the continuous variables just to make sure that we were going to not run into any issues with that. And as I suspected, total volume donated and number of times donating is exactly correlated 100% as we graphed out. So we'll have to keep that in mind when we're running a logistic regression to drop one of those, since it won't work with the singularity. Moving on to the models that I chose. So I first ran a random forest, just because that's one of the first, first ran a bagging model because that's one of the first that I always try. If you go down here, the classification rates, we had a 91% classification rate on the training data, and then an 86% validation or classification rate on the validation data set. But then, as we will see here, the bagging model only produced a log loss score in the driven data scoring model of 0.8796. So this is a common theme that we'll see. But while the models that are with the higher classification rates are also performing the worst on the data or on the driven data test set. The next that I ran was an actual random forest model, so algorithm. So instead of just sampling the population, like the bagging model I'm now sampling the population and the variables being included in the different iterations. This actually, I think, due to the fact that there's not a ton of variables in this data set, we were actually produced the same classification rates with the random forest model as we did with the bagging model. But as you'll see here, the random forest model from a log loss perspective performed a lot better than the bagging model. Moving on, now at this point I'm not getting such great results with the really fancy machine learning algorithms. So sometimes the simplest answer is the best. So I wanted to then just try a simple logistic regression model. As you can see here, ran the regression model on all of the variables except for number of times donating because of the multicollinearity issue. Produced the response variables, which is the probabilities. Then transform the probabilities over to the binary 1 or 0 classifiers, and then ran the confusion matrix on here, the confusion tables on here. On the test data set, it only achieved a 68% classification rate, and then on the validation set, 67%. So at least we have good stability between the outside data. But then, as you'll see here, the logistic regression model actually performed the best out of all the models I performed, with a log loss score of 0.4496. Now, because of the success of the logistic regression model, I did want to try one more advanced technique. So I tried a logit boost model using the ADA package. I ran this a number of different iterations with a number of different iteration numbers here, to try to optimize the log loss function. The training error that was produced here, we've seen that it's a little more optimal at 7 and 14, but for some reason the times that I was getting more optimal results through like really high iteration counts, where they were, the classification rate was in the mid to high 90s for both the train and test data set. Those times weren't performing super well in the log loss function and the scoring. So I chose to utilize 15 iterations for this final model that I would produce. Again, pretty easy to see. Total volume donated, number of times donating are the two most important variables. Here we have, Here we are again producing the classification as well as the probabilities. The classifications allow us to see the classification rate. So here we're at 73%, and then on the validation set we're at actually a little bit better, 76%. So it actually increased performance on the validation set. And then we're able to deploy that model with the probabilities into the log loss scoring model of the driven data, and we achieved a log loss score of 0.4675. So the next thing I would like to run over is how I got these driven data log loss function scores. So as I talked about earlier, I did have to um, rebalance out the data set because the scoring algorithm wouldn't have performed optimally with such an unbalanced data set. So every time that I performed one of the predict functions on the test data, um, and then export it out to a CSV to then upload. I first had to put it through a step to adjust it for the oversampling, so that we weren't overestimating the probabilities of it being a donor. So I achieved this by taking the test data set, the numbers, the exported probability from performing the predict function in R, and then created my own formula created the formula that you can see up here, where it is the um, one plus, and then this is actually what's supposed to be one minus the I can go back. 1 plus 1 divided by the original fraction minus 1 of that's being a 1, so that's 0.24%, divided by 1 divided by the oversampled fraction, so that's 50% minus 1. And then, so I was able to simplify and just have, so the original fraction and the oversampled fraction, I was able to simplify and kind of keep these as static numbers, as you can see, since they're always going to be the same. And then the only one that changes every time is the scoring result. So I put that in here, and then, excuse me, and then was able to, get the adjusted probabilities, and these adjusted probabilities are what we would load into the driven data scoring function. So that's my whole presentation, and thank you very much.